We have already learned about chemical equilibria in the last lecture. And today we're going to dive a bit deeper into equilibrium reactions and learn how we can determine whether our equilibrium reaction is going to yield us more products or more reactants. Let's look at a very general description of a reversible chemical reaction. The reactants, capital A and capital B, with stoichiometric coefficients small a and small b, are reacting to form products C and D. The equilibrium constant K is a value that we use to show the ratio of the concentrations of the products to the concentration of the reactants. It's calculated as the ratio of the equilibrium concentrations of the products raised to the power of their respective stoichiometric coefficients to the equilibrium concentrations of the reactants raised to the power of their stoichiometric coefficients. The value of the equilibrium constant tells us whether we have a higher concentration of products at equilibrium for K larger than 1, or if we have more reactants. In these equilibrium concentration calculations, we define the concentrations of solids, pure liquids, and solvents as 1. So, practically speaking, they're not included in our equilibrium calculations. We can understand this when we consider a solid. If its mass increases, so does its volume. So any change in its concentration is insignificant. Now, what happens when we try to change the conditions of a reaction? For example, by changing the concentration of one of the reactants, the temperature, or by adding a catalyst. The Chatelier's principle tells us that if an equilibrium is disturbed, the position of this equilibrium shifts to counteract the change to re-establish equilibrium. Now, can we understand what that means? Well, say we decrease the temperature at which the reaction is taking place. We then favor the exothermic reaction, which produces heat, over the endothermic reactions, which requires heat. And the system counteracts this change by producing more heat. Let's introduce a new concept, the reaction quotient Q. You see that the equation used to calculate the reaction quotient looks identical to that used to calculate the equilibrium constant K. The main difference is that the equilibrium constant can only be calculated when we are at equilibrium, while the reaction quotient can be calculated whether we are at equilibrium or not. Comparing the value of Q to K tells us in which direction a reaction will shift to reach equilibrium. And we can understand this by looking at what Q would be when we would increase the concentration of hydrogen, when this reaction is already at equilibrium. At equilibrium, this would be how to calculate the equilibrium constant. And when the reaction is not at equilibrium, so for example when we increase the concentration of a reactant, we can calculate the reaction quotient. When we increase the hydrogen concentration, the value of the denominator in this equation increases. And that means, of course, that Q will be a smaller value than K, which tells us that the reaction shifts to the right to reach equilibrium. The forward reaction is favored until equilibrium is reached. And in practice, shifting equilibrium by adding more of a cheap reactant, like what we just did with hydrogen, is a very useful way of converting the maximum amount of the other reactant into the product. And you can imagine this is financially very interesting. For example, if one of the reactants is cheap and the other one is very expensive. I would like to end this lecture by briefly introducing the concept of catalysts. Catalysts are substances that make a reaction go much faster. So you can imagine they're very useful in these large industrial processes where time is money. They do this by lowering the activation energy of the reaction. For example, the cartoon on the right depicts the reaction of ethylene and hydrogen gas. The hydrogen lands on the surface of the catalyst and breaks its bonds. This causes the hydrogen atoms to be bonded to the surface, as you can see in the second image. The double bond of ethylene is also broken, and the two carbon atoms also bond to the surface of the catalyst. Then the hydrogen atoms can migrate until they collide with the bound carbon species, and they react, as you can see in image 4, to form ethane. This ethane can then leave the surface. And what you see is that this catalyst, it stays intact, but it did help to speed up the reaction. And with that, we've already come to the end of this lecture on equilibrium reactions. See you next time for the lecture on chemical technology.